Okay, welcome back. So now today we're going to talk about another type of discrete probability distribution called the geometric distribution. And so we're going to compare some of the things with this one with the last one. So they're similar but different, okay, in some key points. So we're going to start with the conditions. So there are certain conditions that need to be met in order to be a geometric probability distribution, okay? And so here are the conditions. In fact, most of the conditions that we saw with the binomial distribution are also satisfied with the geometric distribution. So first, we have Bernoulli trials. So there's only two possible outcomes for each trial. Bless me. So we only have two possible outcomes. So the other thing is independent trials. So independence also is here. So all trials are independent. Okay. So two possible outcomes for each trial. All trials are independent. And three, the probability of success P is fixed, right? So remember, P equals the probability of a success on each trial, right? So remember, that's going to be given to you, or you have a way of figuring this out, but that's the probability of success. So if I'm talking about a Bernoulli trial, then either I'm going to have a success or a failure. And P is the probability of success. And what we're saying is the probability of a success is the same for each trial. Okay? Now, here's what's different. Where in the binomial case, we only have a fixed number of outcomes. Okay? In the geometric case, we don't have a fixed set of trials. What we're doing is, in this experiment, is we are doing the experiment until we get the first success. Okay? So that's the difference. So 4 is, and I wouldn't quite call it a condition. It's really, really the definition of the random variable. So in this case, x, let me use a different marker. So here x is equal to the number of trials until you get your first success. So we're interested in counting the number of trials until we get our first success. That's the key to a geometric distribution. So all outcomes only have two possible, or all trials only have two possible outcomes. Okay, all the trials are independent of each other, and P is fixed for each trial. Okay, probability of success. And then we're going to define our random variable as we're going to count the number of trials until we get our first success. Okay, so we could get our first success on the first trial, or it could be the second trial, or the third trial. So x, so in other words, x is going to be a count variable, which is going to be part of the set of 1, 2, 3, all the way to whatever n turns out to be, right? So in this case here, with the geometric experiment, you're always going to have n minus 1 failures and then 1 success. Because remember, we're just interested in doing the experiment until we get the first success. So as soon as we get our first success, we're stopping the experiment. Okay? So again, so n can keep going. So hypothetically, n can go off to infinity, so n can't be fixed, okay? Because if I talk, so now here's the thing. Now, a lot of the experiments that we've been doing that are binomial can become geometric by changing x, right? That's really all, it's a binomial experiment, but we're changing what we're defining, how we're defining x, right? In a binomial experiment, x is counting the number of successes out of n trials, so n has to be fixed, okay? But as soon as we say, okay, I just want to know how many trials do I need to do before I get my first success, well, now x is counting that. So now it becomes a geometric distribution. So be careful. You also have to make sure that not only the conditions are met, but hey, how are we defining x, the random variable? Okay, so now just remember also q, so just like before, q is the probability of failure, right? So that's going to equal 1 minus p, the probability of success. Okay, so now how do we denote this? Well, if these are satisfied, and this is how we're defining the random variable, then what we would say is x has a distribution of capital G for geometric, and then again we have the two parameters are going to be P. So it's going to be P. Let me see if I got everything here. Yep, that's it. So it's just going to be P. Because remember, n is not fixed, so the only parameter we're interested in is the probability of a success. So this is going to be what we're going to be interested in. Okay, so now, that's really it. So let's do an experiment, or a problem. Let's do an example, I mean. So here we go. It says you throw a dart at a bullseye until you hit the bullseye. Okay? The first time you hit the bullseye is a success. So if you hit the bullseye and then you throw the dart, it's going to be a success, right? So you could hit the bullseye on the first throw, right? So, or you could hit it on the 10th throw. If you're really bad, maybe 100 throws, okay? So now, let's see here. It might take you 6 times until you hit the bullseye. You can think of the trials as failure, 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 success, and then stop, right? So if I hit the bullseye, I stop, right? It's over. So I'm going until I hit the bullseye. It's like, you know what? I'm going to stand here all day until I hit the bullseye, right? You know people like that? I tend to be that way. I don't want to quit until I at least do it once, right? And then I can say I did it. So this could be a geometric experiment, okay? So there must be at least one trial. Key aspect, right? You have to throw the dart at least once, right? So in theory, the number of trials, again, could go on forever, okay? Let's do this experiment. Let's say we're playing a game. Okay? You play a game of chance that you can either win or lose, and you play until you lose. Okay? Your probability of losing is P equals 0.57. Ooh. So P, remember, is the probability of a success, right? But in this case, we're going until we lose. So in this case, the probability of a success is actually the probability of you losing. So remember what I said about a success is always not always a positive thing, okay? So keep that in mind. So, gotta have my coffee. Okay, so now, here's what we have. Okay, P, I don't like this one either. So P is equal to 0.57. Okay. Now, what else do they tell us there? They're asking, what is the probability that it takes 5 games until you lose? Let X be the number of games you play until you lose. So X equals the number of games until you lose. Okay? So that fits the definition of X for geometric, right? So if we think about this, so we play this game. Let me see. So X also includes, remember, X includes the last game where you won. So it's the total number of trials until you lose. So if you play 6 games, assuming that you lose on the 6th game, so X would be 6, right? So it includes that last game that you lost, okay? So X takes on the value. So what are the possible values of X? Well, X could be at least 1, 2, 3, 4, so on and so forth, right? Could go on, right? You could keep playing, right? You could have a large winning streak, right? Now, what are we looking for here? We want what's the probability that X equals 6, right? So you play 6 games until you lose, right? So you lost on the 6th game, okay? Now, is this a geometric experiment? Does this have a geometric distribution? Let's go through the criteria. Are the games independent of each other? It says you play a game of chance that you could either win or lose, and you play until you lose. Yes, this would be independent, right? Think of a roulette table, right? Or a blackjack table. So these are all games of chance where each play of the game is independent of any other play, right? So we're going to assume that these are independent, so that's good. What's the outcome of each trial, right? Remember, each trial, every time you play the game, what's the outcome? You're either going to lose or you're going to win, right? So there's only 2 possible outcomes. So this is a Bernoulli trial, right? So each trial is Bernoulli. So good. So that one's done. Now, the probability of a success, right? The probability that you lose is 0.57. So that means that, and that's fixed for each one. So we have a fixed probability of success. And as we already discussed, the random variable is defined as counting the number of trials until you have your first success. In this case, until you lose. So it meets all the criteria. So this is a geometric distribution. So what can we say? We could say that X is geometric, and what's P? 0.57. Now, what we didn't discuss is what's the formula for figuring out probability. It's very similar to binomial, except what's different? Well, we already know where the first success is at, right? We already know what we're doing, right? What does this mean? Okay, so let's write this up. This means, right, this is the probability that we won, right, on the first one. So we had a failure. So I'm going to put F for failure, S for success, right? So that means we had a failure on the first trial, failure on the second trial, failure on the third trial, failure on the fourth trial, failure on the fifth trial, and a success on the 6th trial, right? Well, what does this mean? Well, just like we did with binomial, since these are independent events, right? Each game, each trial is independent, we can use the multiplication rule here, right? So we can just use P and Q, right? Remember P and Q? So Q here is equal to what? 0.43, right? So I can say this is equal to the probability of F1 times the probability of F2 times the probability of F3 times the probability of F4 times the probability, of F5 times the probability of S6, right? So what's F? What's the probability of failure? Q. Q times Q times Q times Q times Q times P, right? How many failures did I get? 5. Q, 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 P. What does this equal? Look at that. I get 5 of these and 1 of those. So what do I get? I get Q to the 5th times P to the 1st power. And how many different ways can I get failure, 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 success? There's only one way, right? In fact, no matter what X is, there's only going to be one way of getting that outcome, right? And I hope you see that from our previous videos and previous discussions, okay? So what does this mean? Well, what are we going to do? What's Q? Q is 0.43. So what does this equal? It's going to be 0.43 to the 5th power. So it's going to be 0.43 to the 5th power times what? 0.57. And so what does that equal? Well, let's figure it out. Get your calculator out. I should have had mine out. So now, so 0.43 raised to the 5th power times 0.57, and I get 0.008. So the answer is 0.008. That's it. We're done. So the probability that I play the game 6 times before I lose my first game is 0.008. So a very small probability. Chances are I'm probably going to lose before that, okay, based on what we got here, okay? I hope that makes sense. Oh, hold on, I think. No, I do have it on there. Wasn't sure it was on the video. Okay, so now, what's the takeaway for this? Well, what is the general formula then? Aha! Well, if you haven't figured it out, here it is. So here's the general formula. Okay, so here's the notation, right? So here's X. X is geometric with parameter P, right? So now, what is the probability of X equal to X? Well, it's going to be this. It's going to be the number of failures raised to the n-1 trials, right? Because we're saying every single trial is a failure except for the last one. So n-1. And then followed by P. And that's it. That is the probability of X equal to any specific value of X of a geometric distribution, geometric experiment, okay? So now, let me see here. Let me see what else. Okay, so here are the other notations you need to know. Here's mu. So here's the formula for the mean. Mean of a geometric is just 1 over P. Okay? So it's just 1 over the probability of a success. Okay? The standard deviation, or the variance rather, is going to be this formula. It's going to be 1 over P times 1 over 1 minus P for that. Okay? So to get the variance, you're going to take 1 over p, and then you're going to take 1 over p minus 1 and multiply by that as well. Okay? So this is the variance. And of course, to get standard deviation, it's just the square root of the variance. Okay? So just take this and take the square root of it. I think that's, now I think sometimes different texts will combine these two into one formula. In fact, if you, I believe, some texts will do this. It will be 1 minus p over p, like that. And then what they'll do is multiply through, so it's going to be 1 over p, 1 minus p over p squared. Okay. Some textbooks will do that, but again, either one will give you the same answer. Okay. So if you put all this under one denominator, so you just multiply through, so this would be p over p, so you get 1 minus p over p, and then multiply through by p in the denominator, and you get p squared. So either way, some textbooks, the textbook here does it this way, but again, you could see it in other textbooks differently. So in this case here, it'd just be the square root of 1 over p times 1 over p minus 1, like that. Okay? And that's it. So for a geometric distribution, to find the mean is just 1 over p. To find the variance, it's this formula, and to find the standard deviation, it's this formula. Okay? So let's do another example before we move on. Let's see. Let's see what would be a good one. Here we go. Here we go. Here we go. Here, let's do this one. So it says a safety engineer feels that 25% of all industrial accidents in her plant are caused by failure of employees to follow instructions. She decides to look at the accident reports selected randomly and replaced in the pile after reading. Okay, so with replacement. Until she finds one that shows an accident caused by failure of employees to follow instructions. On average, how many reports would the safety engineer expect to look at until she finds a report showing an accident caused by an employee failure to follow instructions? Okay, so that's the first thing. So here it says she feels that 25% of all industrial accidents in her plant are caused by failure of employees to follow directions. So that's P, right? The probability of an accident is P. So that's the quote-unquote success, right? So P, defined in this case, so P is 0.25, okay? So now, we know that it's going to be geometric. Why? Because it's with replacement. So she's taking a employee accident report randomly out of a pile, looking at it, and then sticking it back in. So the trials are independent. She's only looking for whether the accident report is caused. The accident was caused by failure to follow directions or not. So that's a Bernoulli trial. And she's going to keep looking through the pile until she finds the first accident report where the accident was caused by failure to follow instructions. Okay, so it is a geometric probability distribution or a random variable. Okay, so we know that x is going to be geometric with p equal to 0.25. Okay, now the first thing they're asking us is, what would be the expected number of accident reports that she's going to look through before she finds the first one, or until she finds the first one? Okay, so again, this is just going to be 1 over p. That's it. So what's 1 over p? It's 1 over 0.25, which equals 4. So we would expect that she would have to go through 4 accident reports to find the first one. That's it. You're done. Okay, so you answered the question. Now, what is the probability that the safety engineer will have to examine at least 3 reports until she finds a report showing an accident caused by an employee failure to follow instructions? Well, so at least 3, right? So we want the probability that x is going to be greater than or equal to 3. So she's going to have to go through at least 3 reports to find the first report where the cause of the accident was failure to follow instructions. Okay. Well, how do we find that? Well, let's use our formula, right? This means what? It could be 3, it could be 4, it could be 5, it could be 6. I mean, it can go on forever. So do we really want to do this way? No. In this case, we're going to want to use the complement rule, because if this case, we would have to do the probability of x equal to 3 plus the probability of x equal to 4 plus, and then it could keep going on and on and on, right? So we don't know where to stop. But we know that these probabilities are going to get smaller and smaller and smaller and smaller, okay? So, because remember, the distribution, the whole distribution has the area under the distribution, or the probabilities of the distribution have to equal what? 1. Okay? So, the better way of doing this is, since we already know it, we've already known we have to do at least 3 trials. So why don't we use the complement rule here and say, okay, well, what's 1 minus the probability of being that x is less than 3, okay? Or less than or equal to 2, right? Now, how many probabilities do we have to figure out? Only 2. Probability of x equal 1 and the probability of x equal to 2. And then all we have to do is subtract that probability from 1, and we're done. So now, this is another example where the complement rule helps us out. So this is going 1 minus, now what's the probability of this? This is going to be the probability that x equals what? 1 plus the probability that x equals 2. Okay? So all we have to do is figure out each one of these. So it's going to be 1 minus, and then what's this? This is going to be what? It's just going to be p, right? We got a success on the first trial, so it's just going to be p. This is going to be what? It's going to be q times p, right? Because we're doing 2 trials, failure and then a success, right? So now all we have to do is just plug and chug now. So what's p? 0.25. What's q? 1 minus p, which is 0.75, right? So it's going to be this, 0.25 plus 0.75 times 0.25. And now all we have to do is figure out what that comes out to be. So we get 0.25 plus 0.75 times 0.25, and we get 0.4375. And now all we have to do is subtract that from 1. And we get, obviously, 5625, right? Right? And that's it. We're done. See how easy that was? Now, you could do all of this using the calculator. Okay, so this will be the last thing I'm going to show you. Is on the calculator, you can do the same thing. Just like we had with the binomial, you have a function on your calculator for geometric. Okay, so again, to get to that function, all you have to do is go to second bars, right? So second bars to get to your distribution menu. And then just scroll down until you find what? Either, what is it? It's Geomet. Geomet PDF or Geomet CDF, right? So this here will give us the probability of x equal to a particular value of x, right? Just like binom CDF or PDF. And then this will give us the probability of x being less than or equal to x. So the CDF function, just like binom CDF. So this is the way you would do it in there. Now, what you would have to put into these functions is in this one here, you have to put in p and what your x value is, right? So yeah, so the calculator needs to know what your probability of success is and what x is. And then with the same thing here. So it's p comma x, okay? Okay, so I hope that helps. And this is with for the geometric distribution. Next time, we're going to talk about the Poisson distribution, and that's going to be the last one we're going to talk about in this class, I believe. And that is another discrete probability distribution that comes up quite a bit. Okay, so anyway, I'll see you next time. Okay, welcome back. So here's what we're going to do today. We're going to talk about the next discrete distribution, probability distribution, and that's going to be the Poisson distribution. A Poisson distribution, again, is a discrete probability distribution, and it's going to have certain conditions, just like with the other two that we discussed, the binomial and the geometric. Now we're going to talk about the Poisson. So based on how you define the random variable and what conditions are met, the random variable x will have a Poisson distribution. Okay, so let's first discuss and talk about that. So let me, here we go, let me do this. So let's, where are we at? So what sorts of things will follow a Poisson discrete random variable? Okay, so, or a Poisson distribution. Well, there's a lot of similarities, again, just like with the geometric and binomial. You can also look at and compare the binomial with the Poisson. Okay, you're still counting things. Poisson is about counting things. Okay, so the binomial, the goal is to look at the probability of a specific value of a success out of n objects, right? So x was counting the number of successes out of n objects. Okay, so here's what we're going to do. Now we're going to say a specific number of occurrences. Okay, so with the Poisson, we're dealing with time. Okay, so Poisson is talking about a particular increment of time. So we're counting things, but it's within an interval of time. Okay, so let's say we're interested in counting the number of car accidents at a particular intersection over a 1 hour period of time. or let's say we're looking at the number of people who are on hold in a call queue, let's say at a call center, a customer service call center, and we're interested in the number of people who are on hold at any given period of time, okay? Or the number of people that are standing in line waiting to be helped at the local post office over any given 1 hour period. Each one of those is going to have a Poisson distribution. Okay, so to calculate the probability that X is equal to, right, the number of people or the number of accidents or the number of phone calls, those are all going to be part of a Poisson distribution. Okay, so that's the context. Those are the types of problems that we're going to deal with. Okay, so now here is the Poisson experiment, right? So the first condition that we have is, again, the experiment consists of counting the number of events occurring in a fixed interval of time. So that's the key thing, a fixed interval of time. Okay, whether it's 1 hour, 1 minute, 1 day, it's a fixed interval of time. 12 hours, 6 hours, whatever the case may be. Now it could be a space too, that's the other thing too. It doesn't have to be an increment of time, but it could be space, right? So you could talk about counting the number of bacteria. Oh, maybe that wouldn't be. Would that be a, yeah. So yeah, counting the number of bacteria within a certain area on a petri dish, okay? So a fixed space. Or counting the number of people that live within a geographic region, right? That could also be a Poisson distribution, okay? Let's see here. So now here's the other thing to keep in mind is the experiment consists of counting the number of events occurring in a fixed interval of time or space if these events happen with a known average rate and are independent of the time since the last event. Okay, so let's think about that for a minute. Okay, what does that mean? Okay, so for this case, for this to be a Poisson, what do we need to know? We have to have a fixed interval of time, okay, and each interval of time that we choose, right, is independent of all the other intervals of time, okay? So the rate of the rate of change, or the rate of the number, right? The average rate is going to be independent, is going to be the same and independent of the time since the last event. Okay, so let's write this down. So we're counting the number of events, right? Fixed interval of time or space with a known average rate and independently of the time since the last event. So events. So counting the number of events, okay? That's like the number of phone calls, right? The number of bacteria in an area of a petri dish. The number of accidents or the number of cars that cross a certain intersection, okay? Those are the events that we're counting. Counting the number of events in a fixed, okay, interval of time or space. So that's one thing. So we're counting the number of events, okay, within a particular interval of with a fixed interval of time or space. Okay, with a known average rate. Oh, hold on a second, let me rewrite this. If these events, okay, so here's the conditions. If these events occur with a known average rate, right? So the rate of occurrence, right? So here's the thing, okay, so let's just put an example to this to kind of solidify it in our minds what we're talking about, okay? So let's think of, let's say we have a certain stretch of road, right? So there's our fixed space, right? Let's say we take a randomly selected 1 mile stretch of land, okay? And we take that 1 mile stretch of road and we calculate the rate of the number of cars that go through that 1 mile stretch of land, right? So that's the known rate. So we know, let's say we know that the rate that cars go over that stretch of land or any point of that land is, let's say 36 cars per minute. So that's the known rate. Let's say that's what they're talking about, the average known rate. The average number of cars, for example, that's past a particular point in the road on a particular stretch of land, let's say 1 mile, is 36. 36 cars per minute, okay, on average. Okay? So that's what we mean by the known rate. Okay? Now, we have a fixed interval of time or space. Well, so the 1 mile of road in this example. Okay? Now there's an and here. Okay? So, if these events, right, these events occur with a known average of rate and these events occur independently of the time of the last event. Independent of the time since the last event. Okay, what does that mean? It means that the occurrence of these events are independent of how long it has been since the last event. So, independent of when the last car, or how long it's been since the last car has passed. So, it doesn't matter if the last car passed a minute ago, or if the last car was an hour ago. The occurrence of these events are independent of that. It doesn't matter. Okay? So, that's what this first part means. Okay? Now, 2. The probability of the event remains constant for each interval of equal length. Okay, so let me write that down. Oops. Okay, so the probability of the event, right? So the probability of a car coming down that 1 mile stretch of land, okay, is the same, right? It's constant for each interval of equal length. So what does that mean? If I randomly choose another mile stretch of road, the probability of an event is the same. So regardless of which time interval or space interval I choose, as long as the interval is the same, so fixed, right? Fixed, then the probability of an event will be the same. Okay, that's what that's saying. And then 3. Now, so 3. The number of occurrences in one fixed interval is independent of the number of occurrences in other fixed intervals, right? So what does that mean? It doesn't matter if we chose one interval, right, or one fixed space period, like the 1 mile stretch of land. It doesn't matter what the number of occurrences that happened. It doesn't matter what the number of cars that occurred in this 1 mile stretch that we picked, or that 1 mile stretch. They will have no effect on the number of occurrences that come through the next 1 mile stretch of land that we choose, or road I should say, okay? Or the next time interval. So regardless of what our past experience has been, it has no effect on what the number of occurrences will be in the next time period, okay? So the number of occurrences in one fixed interval of time or space is independent of the number of occurrences in other fixed intervals. And also remember that we're assuming that they're the same sized interval, right? So now, the random variable x, okay, so remember the way we define the random variable is important too. So not only do those conditions need to be met, but here's the way we define the random variable for a Poisson probability distribution. So the x, if you haven't figured it out, it's the number of occurrences within that time period or space, okay? So this is the number of occurrences in the interval of interest. Oops. Okay, that's it. So if it meets these criteria, and this is what we're counting, the number of occurrences in that time interval or space interval, for example, the number of cars that use that 1 mile stretch of land, or that pass over a particular point in that 1 mile stretch of land, or the number of vehicles that use a particular intersection, or the number of phone calls that are on hold for any given 5-minute period of time in a queue, a call queue, right, for a calling center, all of those will satisfy this definition of the random variable, okay? And will satisfy those 3 conditions. And we're going to do some examples so that you can see how they fit or how they satisfy these conditions, okay? So now, let's do this example here so you can see, okay? Now, a book editor might be interested in the number of words spelled incorrectly in a particular book. Okay? It might be that on average there are 5 words spelled incorrectly in 100 pages. The interval is the 100 pages. Okay, so now here this is a space, right? This is not about time, but this is about space, right? So we're talking about the number of the rate in the number of incorrectly spelled words within 100 pages. Excuse me. Within 100 pages. So this would be an example of where x, what are we counting? So let's write this down. So x is what? Well, in this case, what are they interested in? They're interested in the number of incorrect, misspelled words, right? So they're interested in the number of misspelled words within what interval? 100 pages in this book, right? So what are we interested in? The number of occurrences. What is the occurrence? What is the event? A misspelled word. So the number of misspelled words out of what? 100 pages. Or misspelled words in 100 pages of a book. Okay? So this could be a 1,000-page book, right? And what they're saying, hey, is we're interested in how many misspelled words within 100 pages of this book, right? So we're saying regardless of what 100 pages we choose, we're going to count the number of misspelled words within those 100 pages. Make sense? That's what we're doing. Now, what do we know? Well, we know that the average number of words misspelled out of 100 pages is what? It says 5. So the rate, right, the average rate, right, or remember I'm going to use the words known, so known average rate, right? Remember from the conditions? So the known average rate is 5 misspelled words per 100 pages, right? That's the rate. Okay, now, does this fit a Poisson distribution? Yes. So let's go back to the conditions. It says the experiment consists of counting the number of events, misspelled words, occurring in a fixed interval of time or space. Okay, does that fit? Yes. If these events happen with a known average rate of change and they happen independently of the time since the last event. It does. Okay? So we can assume that the events are going to be random. It doesn't matter when the last time we got a word. So if we're scanning for misspelled words, then the next misspelled word that we find is going to be independent of how long it's been since the last time we found a misspelled word. So because, think about it this way. The misspelled words could happen anywhere within the 100 pages, right? There's not going to be any kind of pattern to it, right? So it's not, just because we found one, let's say within the first page, right? That's not going to affect whether we get 3 or 4 or 5 on the next page, or the 3rd page, or the 99th page, right? So it's independent of how long it's been or how many pages it's been since we found the last one. So that condition's met. 2, the probability of the event remains constant for each interval of equal length. Okay, that meets that one. So the probability of an event remains constant. So the interval is 100 pages. And so again, so the probability of the event, so the probability of finding a misspelled word within the 100 pages is the same for each 100 pages. Why? Because they gave us the average rate. Okay? Let's see here. 3, the number of occurrences in one fixed interval is independent of the number of occurrences in another fixed interval. So if we randomly select 100 pages and we find that there was 10 misspelled words in those 100 pages, okay, that's not going to affect the probability of finding a number of occurrences, or it's not going to affect the number of occurrences we find in another randomly selected 100 pages. Okay? So this is an example. In fact, any kind of example that fits this type of scenario is going to be Poisson. Okay? So, what can we deduce from it being a Poisson random variable or a Poisson experiment? Here's what we know. If it is a Poisson experiment, okay, here's the note. Here's what we know. Okay? So, if it's a Poisson experiment, then what do we know? We know X has a Poisson distribution, a Poisson probability distribution. So X is going to be Poisson, capital P, and it's only going to have one parameter that we need to know. Remember, what's the known? What do we need to know? We need to know the average rate, right? So what's the average rate? We're going to denote that by using the mu, okay? So mu, remember average, the average rate is mu. So what is the average number of occurrences? That's the rate. So that is what we're going to use as our parameter. So this is just going to be mu, okay? Now, some textbooks use lambda. Okay, so instead of mu, some textbooks will use lambda. But we're going to use mu. Okay, so just be aware. So now, this textbook we're going to use mu. So now that we know that it has a distribution, we know the parameter, right? Now here's how you calculate mu, variance, and sigma. Okay, so now mu is n times p. Same as the binomial. Okay, so the binomial distribution and the Poisson distribution, the average rate, but the only difference is this mean is the average rate, right? Where in the binomial, that's the average number. Not within a period of time, but out of a fixed number of trials, right? Here, we're talking about a fixed period of time or a fixed space, okay? So, same calculation, but the average means something different, okay? So, variance is equal to mu. Do you see that? So look at that. The variance and the mean are the same. They're always the same. Mu is equal to n times p. The variance is equal to mu, which means the standard deviation is equal to the square root of mu. That's it. And here's the formula for probability. So to calculate the probability, and this is going to be the probability of x is equal to, so x is equal to x. This is the formula. It's going to be mu to the x, or excuse me, mu to the x times e to the negative mu. Okay, so you take the average, raise it to the x power, you multiply it by e raised to the negative average, and then you divide by x factorial. And that's going to give you this probability. So this is the formula that gives you this probability for a Poisson distribution. So again, just like all the other discrete probability distributions, if you want the probability of being, for example, x less than or equal to x, you'd have to do the probability of being equal to x, and then the probability of being equal to x minus 1, all the way down to 0. Okay? Because that's the other thing too, is what are all the possible values of x? Well, in this case, x goes from 0 to infinity. Okay? So very similar to the geometric distribution where x starts at 1. So you have to have the minimum of 1 with the geometric distribution. Here, Poisson, the random variable, can go from 0 to infinity. Okay? So keep that in mind. Other than that, let's do an example. Okay, so here's another example. We're going to work through and calculate some probabilities and see if we can figure out some other calculations. So here it says the average number of loaves of bread put on a shelf in a bakery in a 1/2 hour period of time is 12. So right now, I'm already thinking this is going to be a Poisson random variable because, one, we're talking about a time period, a 12-hour period of time. What are we counting? They're giving us the average number of loaves of bread that are put on a particular shelf over that time period. So this is going to be a Poisson random variable. Okay. Now, it says of interest, here we go. Of interest is the number of loaves of bread put on the shelf in 5 minutes. There you go. We're interested in the number of loaves that are put on that shelf in a 5-minute period of time. Okay? Now, the time interval of interest is 5 minutes. So that's the fixed interval. So within a half an hour, right? So here's the thing. Here's the rate. So think about this for a moment. They give us the known rate of the number of loaves of bread that are put on this shelf in what? A half-hour period of time, right? So a 30-minute period of time. So we know that the average rate that the loaves are put on there is what? What does it say? 12. So on average, they put out 12 loaves of bread on the shelf every 30 minutes. Okay, so let's put that down. Okay, so let's write that down. So what do we know? The rate, the average rate, so that's mu. Mu is equal to what? 12, is it 12? Hold on. Yeah, 12 loaves, right, per what? 30 minutes. So you need to make sure you put the units down correctly, okay? So here's the rate. It's 12 loaves per 30 minutes. So what's the rate per minute. Well, we're going to have to divide that. We're not going to do that now, but just keep that in mind, okay? Because we're going to have loaves per minute, okay? Now, what's the interval of interest, okay? The interval of interest is 5 minutes. So we want to basically take any 5-minute period of time, right? It doesn't matter which 5 minutes. It could be the first 5 minutes, it could be the last 5 minutes, or any 5 minutes in between within the half an hour, right? So, or actually any time during the 12 hours. Is it 12 hours? Let me think. Yeah, in fact, they didn't even tell us it. We're only interested in 5 minutes. So they give us a rate. The rate is per 30 minutes. We're interested in any 5-minute period of time at this bakery. Okay? So now, what is the average number of loaves of bread put on in 5 minutes? So let's think about this. What is the average number of loaves put on the shelf in 5 minutes? Well, what do we know? We know the average number of loaves for every 30 minutes. So what do you think the average number of loaves would be put on there in 5 minutes? Well, all we have to do is find the rate per minute and multiply by what? 5. That's it. So look, this is going to be equal to what? .4. So it's going to be 0.4 loaves per minute. That's the average. So what's the average for every 5 minutes? 5 times this, right? So what's the average number of loaves for every 5-minute interval? Well, it's going to be 0.4 times 5 minutes, right? Which equals 2 loaves for every 5 minutes. That's it. So the answer is 2 loaves. Okay. So now, let's see here. What else do they say here? Okay, so now, since this is a Poisson distribution, how would we do this? Well, now we know how to do the notation, right? Because remember, the rate of change, right, we want the average, right? So what we just found is, hold on a second. Right, so it's based on 5 minutes. So what we just found, this isn't mu, this is the rate. This is the average rate per 30 minutes. Okay, so this is the rate per minute. So mu, right, so this is mu. Sorry, I misspoke. So this is mu because it's based on the interval. That's one thing about this is the known average, right? This is the known rate. Known average rate. Okay? Mu is the average number of occurrences within the specified interval of interest. So we just found mu, okay? Let's see here. Okay, so let's see here. So x here would have a Poisson distribution and mu is 2. And that's how we would use the notation. Okay? So now let's go on. Oh, let me put this down here. So now the next question, now that we know this, right? So now that we know the distribution is Poisson with an average mu of 2, let's answer the question about probability. It says, what is the probability that the number of loaves selected randomly put on the shelf in 5 minutes is 3? So we want to find the probability that the number of loaves that are put on the shelf randomly within a 5-minute period of time is 3. So x is equal to 3. We know that x is Poisson with mu equal to 2. Okay. So what do? Well, this is going to be equal to what? It's going to be equal to mu to the x times e to the negative mu over x factorial. So all we have to do is plug and chug because we know everything now. Mu is 2, so it's going to be 2 raised to the power of x. Well, what's x? 3 times e to the negative 2 over 3 factorial. So all we have to do now is simplify. 2 to the third power is 8 times e to the negative 2 over 3 factorial, which is 6. And so we can stick all of this into our calculator, and what do we get? We get 8 times e to the negative 2 divided by 6, and we get 0.180. And that's the answer. Okay? That's it. So now, if I wanted to find the probability again, just like in the other example with the geometric, let's say I wanted to find out the probability. Let's say I want to find the probability that x is greater than or equal to 3. Well, let's say greater than or equal to 4. Okay, let's say greater than or equal to 4. Okay? Is that what we want? Yeah, let's do that. Okay? So again, remember, what are the values of, what does this mean? It means all values of x, the probability that x is equal to 4 or greater. That means the number of loaves of bread that could be put on the shelf in a 5-minute period of time could be equal to 4, 5, 6, 7, 8, 9, 10, on and on and on and on. So it could hypothetically be infinite. Right now, practically speaking, it's not going to be, but when it comes to probability, we have to consider all the possible values that x could be. Okay? So this, we can't really use the formula because remember, this means that I have to take the probability that x is equal to 4 plus the probability that x is equal to 5, I should say, plus the probability that x is equal to 6, and so on, right? Right? So this is where we're going to use the complement rule again, just like we did with the geometric distribution. So the way I would work this out is I would just use the complement. Well, what's the complement to this? It's going to be 1 minus So the complement of being greater than or equal to 4 is what? Less than or equal to what? 3. So probability of x less than or equal to 3 is what I would use. Okay? So now, I can figure this out easily, right? Because this is going to be the probability that x is equal to 3 plus the probability that x is equal to 2 plus the probability that x is equal to 1 plus the probability that x is equal to 0, right? And so all I have to do is take all of these probabilities, calculate them using the formula that we just used, right? So I'd have to apply the formula to each one of these and then add them up and then take that sum and subtract from 1, okay? So now, just like we would do with the binomial, just like we would do with the geometric, we would do the same thing here. Use the complement rule, okay? And then once you do that, you'd have the answer, okay? Now, there is a function on your calculator that can do this for you, okay? And it's not the geometric, it's the Poisson. So now you have two functions, Poisson PDF, Poisson CDF. So remember, for Poisson, right, we have probability that x is equal to x is going to be what? It's going to be mu to the x times e to the negative mu divided by x factorial, okay? This we can do on the calculator as Poisson PDF. And what you need to put into the calculator is going to be two arguments. You're going to have to put in, is it mu? Hold on a second. No, it's going to be, yeah, it's going to be lambda. So it's going to ask you for two things, lambda and x. But in this case, lambda is the same as mu, okay? So just be aware of that. So it's going to be lambda x, right? So lambda x. So that's what your calculator is going to ask you for. Remember I said some textbooks use lambda versus mu. Well, lambda and mu are the same thing. So remember lambda, that's the Greek letter for lambda, sort of like an upside down y, okay? Is the same as mu. Okay, so the average. So you're going to have to put in the rate, the average rate, based on the time interval. So in the problem that we just did, it was 2 loaves. And then you need to put in the x value, whatever this x value is, and then hit enter. Now for the CDF function, you're going to get this being less than or equal to some value. Okay? So this is going to be Poisson CDF lambda x. Okay? So now, let's calculate this. So, let's say a bank expects to receive 6 bad checks per day on average. Okay? So, a bank expects 6 bad checks per day. Oops. On average. What is the probability of a bank getting fewer than 5 bad checks on any given day. So what's the interval? What's the fixed interval? 1 day, right? Because the average is per day, and they're asking what is the probability that a bank will get fewer than 5 bad checks in a day, right? So right there it's telling you what the interval is. It's 1 day. So this value, 6, is mu in this case, because the interval of interest is 1 day. This is already in the right rate, right? The units. Remember, checks per day, okay? So now we know that 6 is equal to mu. So mu, which is equal to lambda, is 6, okay? So 6 per day, okay? That should make sense. Okay, so now, what do we want? We want, let's see here. Of interest is the number of checks the bank receives in 1 day. So the time interval of interest is 1 day, just like I said. Let x equal the number of bad checks the bank receives in 1 day, right? So x is the number of bad checks per day, right? Or in one, I guess, not per day, in 1 day. Let's just say it that way, okay? Okay, so x, in this case, is going to be a Poisson random variable, okay, because it fits, the scenario fits the conditions. So it's a Poisson random variable. And what's the parameter? Well, 6. So it's going to be P6. So now, let's see. So now let's write what they're looking for. So what are they looking for? Now that we have everything that we need, what do they want? We want to know what's the probability that x is what? It says they want to know the probability, where is it? That they get fewer than 5 checks in a day. So fewer than 5 means less than 5, right? Well, we can't use it the way it is because what do we need? We need less than or equal to. So how can we change this so that it says less than or equal to? Well, easy. This is going to be the same as the probability of being x is less than or equal to what? Oh, hold on. Yeah, so less than or equal to 4. So now it's in the form I need it to be in, so I can use my calculator, right? Because that's what we're going to do. So now I can use my calculator, and what function on the calculator am I going to use? I'm going to use the Poisson CDF function, right? Because it's less than or equal to. Cumulative, right? So now it's going to be the Poisson CDF, and what's the first thing I need to put in? My average, 6. And then comma, the last thing is I need to put in my x value. Well, what x value am I going to put in? 4. Okay, so it's going to be 6 comma 4, and then hit enter, and the answer is going to be 0.2851. And that's it. Okay? So these functions can be used the exact same way that we've done binomial and geometric. So we can calculate things of being greater than or equal to, less than or equal to, and also between by using the same things. Okay? So the techniques are still the same. The conditions are different. The application is different. But again, same idea. Okay? Discrete probability distributions. Okay? So let's see here. Let's do Let's do one more. Okay, here we go. I like this one. Let's do this one. This will be the last one. Okay, so now, let's say we have this. It says, you notice that a newspaper, you notice that a news reporter says, on average, 2 times per broadcast. So you're looking at a particular news reporter, right? And maybe you're one of those people, like I am, when you hear people giving a seminar, and they say all the time, right? What we call fillers. If you ever take a speech class, that's one of the things that in speech class you learn to pay attention to, so that you don't use fillers when you're trying to fill an empty space. So this particular news reporter says, on average, 2 times per broadcast. What is the probability that the news reporter says, more than 2 times per broadcast? So now, here are the questions. Or excuse me, let me read further. It says, this is a Poisson problem because you're interested in knowing the number of times the news reporter says during a broadcast. So this has to be a Poisson random variable because of that. Okay? Pay attention to that. So now let's answer these questions. A, what is the interval of interest? So what is the interval of interest? In this case, it's going to be 1 broadcast. Because what are we interested in? We're interested in the number of what? Right? In what? 1 broadcast. So the interval of interest is 1 broadcast, right? So whether that broadcast is half an hour every day or whatever, but that's what we're interested in. So, B, what is the average number of times the news reporter says during 1 broadcast? Well, I didn't write it down. Well, it says that the reporter says an average of how many times per broadcast? 2. So the answer is 2. So mu is equal to 2. So A, so we know that X is Poisson, and the parameter is 2, right? So A is going to be 1 broadcast. That's the interval of interest, 1 broadcast. And B, we said mu was equal to 2. Now, C says, what does X represent? Well, we already talked about that. So X equals the number of, I guess you say it that way. The number of during 1 broadcast. Okay? So that's going to be X. And of course, D says write the mathematical statement for the probability question. Okay, so the mathematical statement for the probability question is going to be what? Well, what's the probability question? What's the probability that the news reporter says more than 2 times per broadcast? So the way we would write the probability statement in mathematical symbols is P that X is what? More than, so that's going to be greater than what? 2. That's it. Okay? So now, E, find the probability that the news reporter says more than 2 times per broadcast. Well, in this case, if we're going to use the calculator, right? Well, if we were going to use the formula, what would we do? We'd have to use the complement rule here. And we'd have to write this as 1 minus the probability that X is what? Less than or equal to what? 2, right? Because this is greater than 2, which means 3 or more. So the complement to greater than 2 has to be less than or equal to 2. Okay? Now we could use the formula for X is equal to 0 plus X is equal to 1 plus the probability that X is equal to 3. And then add those together here and then subtract that sum from 1. But if we're going to use the calculator, we still can't use it in this form because remember, the calculator needs less than or equal to. So again, we're still going to use the complement rule. So it's still going to be 1 minus the probability that X is less than or equal to 2. But now we can use the calculator because it's in the right form. And what's the function in our calculator? It's going to be Poisson CDF, right? So it's going to be 1 minus Poisson CDF. And what are we going to put in? Well, we need to put in the parameter and then our X value. What's the parameter? 2. So mu is 2, or lambda is 2, followed by X. What's X? X is also 2. So now, let's go to the calculator. And here's how you do it on the calculator. You're going to go to your distribution menu. So don't forget, so you're going to go to second. Vars. And then you're going to go to your distribution menu, which you'll already be on there. And then you're going to scroll down to, well, either the Poisson, PDF, and CDF. So you're going to scroll down to, in this case, Poisson CDF, and then you just enter in your information. Oops. And CDF, and you're going to put in 2, 2. And what do you get when you do that? Let's do it. Okay, so I'm going to go second vars, and I'm going to scroll all the way down until I find Poisson CDF, which is letter D on my calculator. Hit enter. Now I'm going to put in 2, 2. Hit enter. 0.677. So it's going to be 1 minus 0.677, and so the final probability is going to be 0.323. So the probability that we get more than 2, what are we counting again? 2 us, right? So the probability that the reporter has more than 2 us within one broadcast is 0.323. And that's it. Let's see here. Okay, well, I'll end it there. But again, do some of the other examples in the textbook or in the PowerPoint presentations, but these should give you an idea of how to handle a Poisson, especially how to recognize a Poisson experiment and how to handle a Poisson experiment. First of all, making sure you understand what mu is. Remember, mu is always the average rate based on the interval, right? So it's always the rate based on the interval of time or space, okay? Once you know mu, okay, and you know that x is the Poisson random variable, then you just apply the formula or use the function in your calculator to calculate probabilities. Remember the formulas for finding the average, mu, right? So once you know mu, then you also know what the standard deviation is, or the variance rather, okay? So mu and this variance are always the same for a Poisson random variable or a Poisson experiment, okay? And then you just take the square root of mu to get the standard deviation. So, and that's it. And then mu also is just n times p if you know the probability of success or the probability of an event. Okay, it's just n times p. I'm going to double check that because it doesn't sound right to me that they put that in there. But I'll double check that and correct that. But that's what they're saying here. It makes sense, but then they don't really define what p is. So most of the time in a Poisson experiment, they're going to give you the average rate. So I'm not sure where p is coming from. Just so hold off on that part, but it should be fine. Okay, that's it. I'll see you next time. Have a good day.